All right. Chapter 9 is all about this idea of piecewise functions. And piecewise is a type of function defined by at least two different equations or pieces. That's why it's called a piecewise. There's two separate equations. And if you look down here, you can see an example of a piecewise function. So you have the function name right here. You have a kind of a braces right here indicating which separate functions are involved in this function, or separate equations involved in this function. And then over here you have intervals. We call them domain intervals that tell you when to use which equation at certain times. So a piecewise function is a function defined by at least two different equations, and this one has three, with each piece signed a different interval. These are your different intervals. So down on example 1, we're going to learn how to evaluate these piecewise functions, and I have kind of 4 easy steps to follow to evaluating piecewise. The first thing you're going to do is you're going to match the x value given in the question to one of the interval domains. So if you look here on my example here, it says find f of negative 3. So you're going to go to the f function, and the first thing you're going to do is consider which interval negative 3 is a part of. Is it a part of interval number 1, 2, or 3? And negative 3 is a part of the second interval. That's part number 1. Match the x value with the interval domains. Then use the equation associated with that interval domain. So since we're on interval domain number 2 as my numbering, using my numbering, we're going to use this equation right here to evaluate negative 3. Step 3 says plug the x value into the equation associated with that domain. So we're going to plug it into this equation. Negative 3 goes right here. And then we'll just evaluate it down to the answer of 8. That's piecewise. Now, our example 1 is going to have much easier equations than will example 2 and 3. So let's go right away. So it says here h at negative 1. All right, which interval is negative 1 a part of? Is it part of interval 1, 2, 3, or 4? And I'm just numbering that so I can talk about which interval and you could understand which one I'm talking about. On your homework, they won't number them. So negative 1 looks like it appears to be either 1 or 2 because negative 1 is part of this interval from negative 2 to negative 1. And negative 1 to 0 is this interval here. But it's going to be part of 1 because it says here that it's equal to negative 1. So it's going to be part of this interval. So h at negative 1 is just negative 1. There's no equation to plug it in, so it's just going to be the number that's sitting right there. All right, h at negative 1, so we'll go to the h function. We'll first consider which interval domains. And it looks like 1 is a part of interval 3 and interval 4. But since it's equal to 1 on interval 3 and it's just greater than 1 on interval 4, we're actually going to use the third interval right here as your answer. So then we'll use just 1 here as our answer. All right, you guys do example B here. All right, h at 0. I'm going to go ahead and number them again too so we can discuss which ones we're talking about. So h at 0, we're going to consider which interval domain it's a part of. It could be a part of 2 or 3, but it's going to be 2 because it's equal to 0. So the answer to this one is 0. Interval domain for 2, it's right here. There's only one of them, and it's equal to, so the answer is going to be just 2. Okay? All right, just more examples with these piecewise. So it says g of -8. And if I look at my interval notation, it gives me either not 2 or 2. And the only time that this is going to be -2, I guess, and I said 2, it's -2, is going to be on this case right over here. So is -8 part of not 2, or is it part of 2? It's going to be part of not 2, which means we're going to use this equation then, and we're going to plug in -8 and evaluate it. So cancel here, we got a -2. This will be a 6 minus 2 equals 4. So the answer to this is 4. Is -2, because they want g of -2, is -2 part of 2 or not 2? -2. It's a part of -2. So the answer is just going to be 3. There's no variables in this, so it's just straight constant value. All right, you guys do letter B. All right, is -1 part of not -1 or part of actual -1? And looks like it's going to be part of actual -1, so the answer to the first one is 2. Is 4 part of -1 or not -1? I think it's part of not -1, so for this one we'll use this equation, -1/4 times 4 plus 2. Cancel the 4, -1 plus 2 is just 1. All right, we got 3 intervals now. First question is just 4. So the one interval is less than -1, then from -1 to 2, and then anything greater than 2. And so if I number these just for conversation purposes, 4 is going to be a part of interval number 3 because it's greater than 2. So we're going to use this equation, -1/2 times 4 minus 1. We'll just cancel here to get 2. So this would give us -2 minus 1, which is -3. -1 Well, there's two sections where -1 could be, but it's going to have to be the second one because it's here where x is actually equal to -1. Up here, it's just x is less than but not equal to -1. So it's going to be interval number 2. So we're going to need this guy right here. Bring it down. So -1 minus 1 squared plus 3. -2 squared plus 3. We got to take the square first, so -4 plus 3 and -1. Okay, you guys do letter D. All right, -4. 1, 2, 3. -4 is going to be part of the x is greater than 2 interval, so interval number 3. So we're going to take this equation, 1/4 times -4 minus 2. Double check that here. -4. Is -4 part of this interval or top part of the first interval? First one, okay. +4 would be part of this interval. My bad. So we're going to take this interval instead down. It'll be 1/4 this. It's +2, so I was really close. Thank goodness the error was minor. All right, so we'll cancel here. This leaves me with -1. -1 plus 2. Or just 1. All right, is 2 part of interval 2 or part of interval 3? I think this one is part of interval 3. So this one actually is the one that's going to go down. 1/4 times 2 minus 2. Cancel just a little bit, so we're going to end up with 1/2 minus 2. 1/2 minus 4/2, which is 3/2, so -3/2. Or 1 and 1/2. All right. Okay, piecewise graphing. So now we're all about graphing. And I have 3 graphing considerations. You got to consider 3 things to get these things graphed correctly. The first thing you need to consider is the boundary of each piece, and you're going to do that based on the domains, and that's these guys back here on the right-hand side. These are your domains. So you're going to consider boundaries. Number 2, you're going to consider opened or closed circles. So you're going to consider open or closed circles based on the greater than, less than signs, or greater than or equal to signs, and less than or equal to signs. And essentially, this is how it works. If you have a greater than, or this would be a less than or greater than, you're going to use open circle. If you have less than or equal to, or greater than or equal to, you used a filled in circle like this. So open versus filled in. All right, so if I look at example 3 here, some of these will have open circles and closed circles. So this one right here is going to be open because it's just less than. This one is going to be closed because it's equal to. And this one here is going to be open because it's greater than. The last consideration I have is consider the graph of each piece. And these are graphs right here. And all the graphs are y equals mx plus b, or y equals x squared, or some quadratic. It's literally some equation that can be graphed inside the graph paper. The first couple examples, though, are just horizontal lines. They're very simple graphs. Y equals a number, which is just a horizontal line. But in the 4th and 5th examples, they're going to be more like these linear equations that you're going to have to remember how to graph, using a T-chart or using M and B's from when we learned how to graph equations. All right. So those are my 3 considerations. So we're going to consider the intervals, we're going to consider open and closed circles, and then we'll consider the graphs. And we're only going to graph the graph within the interval it gives us. So on this example, there's really only one kind of major boundary, and that's here at 1. Everything kind of revolves around that point. When x is less than this interval, the answer is 2, and it's an open circle. So we're going to put an open circle here at the beginning of our interval, which is at 1, and we're just going to graph straight over here. It's just a boring old horizontal line. But it terminates at 1 according to this interval. Then at 1, it's at -3. So we'll just put a single dot here at -3 because it's only -3 when x equals 1. So it's not anywhere else except when x equals 1. And then once it gets larger than 1, it jumps up to just -1. So I'm going to open up a circle there, and it's going to go this direction. And that right there is the graph. All right, mine had 3, yours only had 2, and it looks like everything was pivoting off and around 0. So, your pivot line is right here at 0, your interval domain. And when it is literally 0, this is going to be your closed point, it's at -1. When it's not 0, then it's -3. So we'll go down here to not 0. We're going to put an open circle because you have to put an open circle because at 0, it's actually -1. But when it is not 0 and it's anything else, the graph is this guy right here. Okay. All right. So same idea here. We have interval notation over here, interval domains. In here we have equations, but the equations are still just numbers, so they're going to be horizontal lines. And this time we have 4 intervals. So we start at -2, and from -2 to 1, -1, it's going to be at -3. So over here we have a closed circle. That's because it's equal to. And over here we have an open because it's just not equal to. Okay, so we'll go here to -2. We'll put a closed circle there. We'll put an open circle here, and it's going to be at -3 during that interval right there. The second one here is it goes from -1 to 0. It's closed at -1, and it's open at 0, and the line is just -2. Okay, then for the third one, we'll go from 0 to 1 at -1. So we're going to close circle, open circle. And then again at 0 from 1 to 2, we're going to close circle, open circle. And then anything to the right of 2 and to the left of -2 is just not defined by this function. So we don't know what happens outside those domain values. All right, you guys do this. All right, from -3 to 2, first with an open circle, and then a closed circle. So it's kind of the opposite of what we had over there. It's going to be -2. So we'll go down here to -2, go over here to 3, and it's going to be an open to a closed. Then at 1, it's going to be open to a closed, open to a closed, open to a closed, like that. Some actually call this step piecewise because they kind of look like steps. So, all right, now we're going to graph linear piecewise. They look like this over here. And they're not horizontal. The reason they're not horizontal like the last two examples is because there's a variable and other things going along with each of these equations. And both of these equations can be written in just normal y equals mx plus b and graphed like y equals mx plus b. And we're only graphing each of the equations within its interval domain. And so while this equation right here, which happens to be the top equation, while we would normally just graph it all the way through with arrows on both ends, it terminates at -2. So it starts at -2, and this is the way you graph it, but it terminates here. And then it jumps down to this guy down here as the graph for the second equation. And it starts with an open circle because it's not equal to. So it's open circle for this one, and then the graph goes down. Now, it's usually easier to graph the graph that goes through the b value because you can easily identify the b value on this guy as 3. So I put a dot at 3, and the slope here is 1 to 1. So I go up 1 over 1, up 1 over 1. I can kind of just draw it here and then go back to where the interval center is or where the domain interval terminates. These down here, where you have to kind of start but not put any points, it becomes a little bit more tricky because you have to start, for this one, you'd start at +1, and then you would need to go down at a slope of 3, so you'd go down 1, 2, 3, and over 1, still not put a point, down 3, over 1, and then finally put your open circle at the start of the interval. So there's a bit of a trick to pulling this off. So you're going to identify the boundaries, that's these guys, determine how each equation is graphed. All right, some like to graph it and then erase it later, and maybe I'll do that if I can find a pencil. So determine how each equation is graphed, and then just graph the part within the boundaries. And then determine if it's continuous or not. And it's going to be continuous if the graph doesn't jump like this guy does. So there's actually a gap here between this point and this point. So we'd actually say this one is not continuous. All right. All right, so we got 4 examples here. I'm going to grab a pencil so I can erase it. All right, so we're going to graph this function. It looks very similar to the one I just did on the other page. There's a slight variation to it, but not much. So we're going to graph the first one. It says when x is less than -2. And -2, I'm just going to kind of put like a little bit of a dotted line here just to indicate that things are going to be different on the left of that dotted line than it is on the right side of that dotted line. So things are a little bit different. And we're going to graph y equals 3x plus 1. Y equals 3x plus 1. So I'm going to graph the whole equation. So I'm going to go up here to 1, put a dot. And we'll have a slope of up 3, 1, 2, 3, and we always go up and to the right since it's positive, 3 up, and then now I'm going to continue going down 3, 1, 2, 3 over 1, down 3 over 1, down 3 over 1, and here we are. I'm going to go ahead and graph this. I do still have my straight edge. I'm going to go ahead and graph this right here. So this would be the whole line if we graphed that whole line right there. That's where it would be. But we don't graph the whole line. We actually graph just part of the line. So we're going to graph just the part that is less than -2. So here's -2. I'm going to put an open circle right here. And the graph is just this section down here. And I'm going to erase this part because it's not within the domain. All right, and I do that so you can see that the graph actually goes all the way through, but we're only going to look at the part that happens to be associated with our domain. All right, so let's do the same thing for x minus 3. So this is y equals x minus 3. So we're going to go down 3 units here and put our b values. So 1, 2, 3 right there. And this guy says that it's a 1-to-1 slope. So up 1 over 1, up 1 over 1. And the slope goes like this. Okay? So if I were to graph this one, it would look like this. All right, so notice that I graphed the whole entire line, but we can't. We can only graph the part that are greater than 2. So this whole part over here needs to go away. And we're only going to start with a full dot right here. And it happens to be on the same spot where the other one terminated. And it goes like this. And then I need to erase this part right there. And that right there is your graph. It goes down during this interval, like steeper, and then less steep for this interval. So it breaks at -2 because we have a different function here. So is the function continuous? In this case, it is continuous. All right, I'm going to do letter C because I know this one is not continuous, so I want to give you an example of a non-continuous one as opposed to giving you 2 continuous ones and sending you on 2 non-continuous ones. All right, this one here has its boundary set at 1. So I'm going to kind of put a dotted line there just to remind myself where the boundary is. And the graph is going to be very different on the left than it is on the right. So when x is less than 1, it's going to be this guy. So we're going to do the first one, the top one, y equals 5x minus 1. 5x minus 4, that is. 5x minus 4, it's that equation. So we're going to go down and put a dot here at 4. And it's going to be a super steep slope, 5-to-1 ratio from this b value. So 1, 2, 3, 4, 5, and over 1. And then down 1, 2, 3, 4, 5 over 1. And this guy is going to be super, super steep here, like that. That's the whole line. Now, we're not graphing the whole line. We're only wanting to graph the section where it's less than 1. So less than 1 is going to be just the steep left-hand side part right here. And so I'm going to go ahead and erase this section because this is not part of it. And I'm going to put a solid dot here because it is equal to up there in the domain. All right, let's do the second one. Up 4, put a dot. And this one has a slope of -1 to 1. So I always say, always go up, and then since it's negative, we'll go to the right. Always go up to the right. Once you have established the direction, you're going to go down into the, so did I say up to the right? Up to the left because it's negative, and then down to the right to show that the equation actually runs like this. Okay. That's the full line right there. But we're not going to actually graph the full line. We only graph the section that is to the right of 1. So I'm going to put a open circle dot here and only consider the parts to the right. And I'm going to erase everything to the left. There should never be any overlap vertically on this graph. It should be only, you should be able to draw a vertical line at any point on this graph and it never crosses it twice. All right, that's function notation. It's called the vertical lines test. So if you have part of your graph that goes in to the wrong part, you would be able to just draw a line through one section and a second section if you don't erase the proper part. And by the way, is this one continuous or not continuous? It's not continuous. It actually breaks right there for a little bit. All right, you guys do letter B, then I will do it. Then you guys do letter C, and then I will do it so we can check your work, okay? All right, I'll give you about 4 minutes. All right, so back to my pencil so I can erase. So our boundary on this one here is at 2. And we're going to be graphing y equals negative 2x plus 3. So I'm going to go up to 3, put a dot. And then it's a slope of negative 2. I'm going to go up 2 and to the left since it's negative, up 2 and to the left because it's negative. And then I need to go towards my boundary, so I'm going to go down 2 and over, down 2 and over, down 2 and over. There it is. And then take my straight edge. And the whole line is this. That's the whole line. But I only need to keep the part that's left of the 2 with an open circle. So it's going to go right here, open circle, not closed. Make sure that puppy is open. And I'm going to need to erase all of this down here because I don't want anything to the right of that boundary line. So the only part that we need is this guy right here. Y equals x minus 3. So we're going to go to negative 3 here. There's negative 3. And it's a 1-to-1 ratio. So we'll go up 1 over 1, up 1 over 1. And it happens to go right through the dot we just made. So the full line here is that guy right there. And if I just left it like that, it would actually fail the vertical lines test. Like I could draw a vertical line here and it would hit 2 lines. If I ever can do that, that means you didn't graph it right. They're both going the same direction. Because once in a while, I'll get kids that do a line here, and then they'll erase this section here. And then it'll draw this and go this direction. And I'm like, well, that doesn't make sense because both of them are to the left of the 2. And it would fail the vertical lines test. The section that we want to keep is this section over here. Now, it's a filled-in dot. I know it's filling in that closed dot I just made, but that's okay. And this guy goes up like that, and I need to erase or rid myself of this section there. That is your graph there, that V shape. And is this continuous? Absolutely continuous. All right, you guys do this one here. This one's going to be broken. All right. Our boundary on this one here is 2. And we're going to graph this first one here starting at 3. And it has a -5 slope, so it's going to be very steep. So up 5, 1, 2, 3, 4, 4, 5. Over to the left one because it's negative. And then I'm going to run out of room, so I'll go down 1, 2, 3, 4, 5 over 1. And then 1, 2, 3, 4, 5 and over 1. And we're at the boundary line. And I'll go ahead and put a full circle there because I know it's going to be a full circle. And the whole graph is this guy right there, but we only want the part to the left of the 2, so I'll go ahead and just right away erase this section here. So our dot goes this way. All right, for the second one here, it's going to be at -4 here. And it's going to be an up 1 over 1 relationship. So up 1 dot, up 1 over 1, up 1 over 1. And the line goes this direction. Like that. And we're only going to want the section to the right. So I'm going to have to erase everything to the left. Because if I kept that section to the left, it would fail the vertical lines test. And the vertical lines test is that it can't cross at 2 places. All right, so I'll erase just that part. And that's your full graph right there. At no point can you draw a vertical line where it crosses twice, so you know you have it done right. Now, is this continuous or not continuous? It's not continuous. Here we go.